right, let's just get right into it. We have all been there. You're staring at a plant in some windowless office, under the hum of those fluorescent lights, and you just have to wonder, is this thing actually living or is it just dying in super slow motion? Well, today we're going to settle that debate once and for all with science. I mean, it's a question that comes from a place of real-world experience, right? You see those leaves starting to turn yellow, the fact that there's no new growth, and you can't help but feel just a little bit guilty. Can that generic ceiling light fixture really be enough to sustain a life? And here's where we get our first big twist. From a pure physics point of view, the answer is a big, loud yes. See, thanks to something called the Stark-Einstein law, a plant's chlorophyll really doesn't care if a photon comes from the giant fusion reactor in the sky or from a fluorescent tube. To the plant, a photon is a photon. So technically, yes, that light is causing photosynthesis. Case closed, right? No, not even close. The fact that photosynthesis is possible is completely beside the point. The real question here isn't about physics, it's about economics. Plant economics. Is the plant making more energy than it's burning just to stay alive every day? This is really a battle of metabolic survival. Okay, so to really understand this battle, we have to unlearn something pretty fundamental about light itself. Because the way you and I perceive brightness has almost nothing to do with how a plant actually eats it. So here's the key idea. We measure brightness in a unit called lux, which is a scale designed specifically for human eyes. And our eyes are most sensitive to green light. But plants, they don't see light, they eat it. Their fuel is measured in something totally different called ppfd, which basically just counts the number of useful photons smacking into the leaves. This means a room can look incredibly bright to us, because it's just flooded with that green light our eyes love, but for a plant, it could be a total starvation diet. And that brings us to maybe the single most important concept for this whole investigation, the light compensation point, or LCP. Just think of it like a metabolic break-even point for the plant. If the light intensity is above its LCP, hey, the plant is turning a profit for the day. But if it's below that line, the plant is going into debt. It's burning through its own reserves and slowly, literally cannibalizing itself just to survive. All right, so to see how this all plays out in the real world, let's stage a little showdown, shall we? We'll pit two of the most common office plants against each other, and each one has a radically different strategy for survival. In this corner, we have the undisputed champion of low-light survival, the snake plant. Its secret weapon is this incredible superpower called CAM photosynthesis. Now, what it does is so clever. It opens its pores and breathes in all the CO2 it needs during the night, and then it stores it as an acid. Then during the day, it seals up its pores to save water and just uses whatever pathetic little bit of light is available to process that stored CO2. It's like a CO2 battery, which makes it unbelievably efficient. Its energy needs are just ridiculously low. And in the other corner, we have the beautiful, but let's be honest, high-maintenance Areca Palm. It uses the standard run-of-the-mill C3 photosynthesis, which means it has to take in light and CO2 at the exact same time. But here's its fatal flaw. In low light, the main enzyme that runs the show gets confused. It accidentally starts grabbing oxygen molecules instead of CO2. This whole process is called photorespiration, and you can think of it as a massive energy leak. It's actively wasting the precious little energy the plant is making. Okay, so we have our contenders. Now, let's take a hard look at the arena itself, the typical office environment. What kind of light are we actually serving up here? What's really fascinating about fluorescent light is its spectrum. It isn't a nice, smooth rainbow like sunlight. No, it's a series of really sharp, distinct spikes. It has a huge peak in the green part of the spectrum, on purpose, to look bright to our eyes. But it also has a pretty strong spike in the blue range. And that blue light, well, it's actually pretty good for keeping foliage green and compact. So that's one small point in its favor. But here's the number that changes everything. The official lighting standard for most office desks is about 500 lux. Now, this level was set for human comfort. It's designed to help us read and to prevent glare on our computer screens. It was never, ever, not for 1 second, designed with a plant's metabolic needs in mind. Okay, this is it. The moment of truth. We know what the plants need, and we know what the office is actually providing. So let's put the numbers together and see who survives. This table right here, it shows what that 500 lux really means in terms of plant fuel. And the numbers are just shocking. That standard desk light provides a tiny, tiny trickle of energy, about 6.75 units of that ppfd we talked about. Over a whole day, that adds up to something called a daily light interval of just 0.24.
Now, to put that in perspective, even what a professional grower would call a low-light environment provides 10 times that amount of energy.
And this chart just lays out the brutal reality. I mean, look at that tiny little bar on the left. That's the daily energy budget from a standard office desk, just 0.24. For the snake plant, you know what? That's enough to get by. But look at the bar right next to it. The Areca Palm needs a DLI of at least 1.0 just to break even. The office isn't providing even a quarter of what it needs to simply survive.
So the results are in. What does this all actually mean for that plant sitting on your desk or tucked away in the corner of your office? Let's break down the practical takeaways. Here's how you can tell what's really going on just by looking. A starving snake plant, it just stops. It goes into total stasis. It won't grow, but its leaves will stay a deep, dark green as it tries to maximize every little bit of chlorophyll it has. A starving Areca palm, on the other hand, is way more dramatic. It starts cannibalizing its oldest, lowest leaves, turning them yellow as it desperately pulls nutrients from them to send any new growth. So for the snake plant, the advice is actually pretty simple. Get it off the floor and put it on a desk to get it closer to the light source. That standard office lighting, it's genuinely fine for its long-term survival. The biggest mistake you can make is overwatering it, because in this low energy state, it's barely using any water at all. Just expect it to persist, not to put on a big show of growth. Now for the Areca palm, the situation is basically an emergency. That overhead ceiling light alone is a death sentence. It absolutely needs a dedicated lamp placed within about 24 inches of its leaves. You've got to rotate it every week so all sides get a fighting chance. And this is crucial. Stop fertilizing it. You can't force feed a starving plant. You're just poisoning the soil. And this really brings us to the final, powerful verdict from all this research. The very same fluorescent light that provides a sustainable, long-term habitat for that super efficient snake plant is nothing more than a hospice for the Areca palm, a place where it might look okay for a little while, but it is slowly and inevitably dying. So now you know. The critical difference isn't the light, it's the plant's strategy. And the next time you walk through an office, you're not going to see a collection of green decor anymore. You're going to see a series of tiny, silent metabolic battles being won and being lost. And you'll be able to look at any plant and know the answer to the real question. Is it living there, or is it just waiting to die?